We are now going to start a chapter about linear regression. Our main goal is to discover whether there is a linear relationship between two random variables, x and y. And that linear relationship will be y equals beta 0, which is an intercept, plus beta 1, which is going to be a slope, times x plus epsilon. So beta 0 and beta 1 are unknown parameters. And epsilon is a random variable for the air. That will become more clear later as we go through this lesson. So what do I mean by linear relationship? Well, let's consider these two scatter plots. The first scatter plot is of the global change in temperature versus CO2 levels in the atmosphere in parts per million. And you'll notice that as the CO2 concentration increases, that the change in global temperature also increases, and there seems to be an approximate linear relationship. So this has a linear relationship. But I'll show you a different data set of college GPAs versus the verbal section from the SAT or the English section from the SAT. And you'll notice that there doesn't seem to be any sort of relationship between college GPA and SAT verbal. There are people with high SAT verbal and high college GPA, but there are also people with low SAT verbal scores and still relatively high college GPAs. So this does not seem to have a linear relationship. So let's explore further what I mean by a linear relationship. So let's look at an example of heights and weights. So we're going to let x be the height and y be the weight of a population of adult males. We expect, right, that as people are taller, that they will end up being heavier. So there should be some sort of relationship between height and weight. In fact, for each height x equals some little x, then there's a conditional distribution of weights y. What I mean by this is, imagine that you have someone that's 6 feet tall or 72 inches tall. Then you don't expect every adult male who is 72 inches tall to be the same height. You expect that there should be some sort of, say, normal distribution of weights for all males that are 72 inches tall. Then if you look at males that are, say, 68 inches tall, you again don't expect them all to weigh the same. You expect there to be some sort of normal distribution where there's a mean for every adult male that's 68 inches tall, and then there's some sort of standard deviation of weights. Some people weigh less, some people weigh more. So since there's a conditional distribution of weights, y, for every input x, we can look at the expected value of that distribution. So the expected value of y, if there's a linear relationship, should be the expected value of beta 0 plus beta 1 times x plus epsilon. And notice that I've put in a lowercase x because this is a conditional distribution, and I'm assuming that capital X equals little x. So if we look at the expected value, in fact, we actually just have the expected value of the constant b0 plus the expected value of the constant b1, beta 1 x, and then the expected value of epsilon, which is the random error. And we're going to actually define epsilon, so its expected value is 0. So that the expected value of y given x is just beta 0 plus beta 1 x. It's just a line. So the expected value stands for the mean weight of men who are x inches tall. So what we're saying is that this line, beta 0 plus beta 1x, gives us all of the mean weights of men who are x inches tall. So in fact, the line is the mean. Now let's look at the variance of y. Well, that would be the variance of beta 0 plus beta 1 x plus epsilon. Again, we're going to substitute capital X equals little x there. And then notice that beta 0 plus beta 1x, that's just a constant. So if we shift epsilon by that constant, then the variance of beta 0 plus beta 1x plus epsilon should just be the variance of epsilon, because that's the only random variable that we see here. And then we're again going to define this epsilon so that the variance is equal to sigma squared. Okay, so this is going to be by definition. And so then what does the variance mean? So this is the variance of weights for men who are x inches tall. So let's get an understanding of what I mean by looking at this example. We'll consider a fictitious population of adult men below. And so you'll notice I'll have a height, x, ranging from 64 inches to 76 inches. And then I've listed their weights, their average weights for each height. So the average weight for 64 inches tall is 127 pounds. Okay, and then the average weight for someone who's 72 inches tall or 6 feet tall is 161 pounds. And then the idea is that for each height, the weight has some sort of distribution, right? The distribution has a mean given by that weight column, but it also has a standard deviation. In each case, we're going to say that the standard deviation is 20 pounds for each height. Okay, we should note that the standard deviation is constant because that's actually important for our model. And then I want you to look at this plot. Okay, notice again for people who are 6 feet tall or 72 inches that there's a mean for their weight. Okay, but then you can see kind of a normal distribution of heights. Okay, some people who are 72 inches tall are going to weigh more, going to weigh closer to 200 pounds. Okay, some people who are 72 inches tall are going to be way less, maybe closer to, say, 140 pounds, right? There's a distribution of weights. In fact, for each of the heights, you can see a nice distribution of weights. And what's important is that you can see that the line actually gives the average weight for each one of the heights. So you can see the average weight lies right on that line, giving the linear relationship. So when you're looking at a line like this, so you're looking at, say, y equals beta 0 plus beta 1 x plus epsilon, you should think of the line as being the mean. So sometimes we could call that mu y given x. And then the epsilon, that's the random error. That's what's giving the normal distribution around each height. Because we don't expect people who are the same height to always be the same weight. There should be some sort of normal distribution of weights for each height. Now, if you look at if you look at this this table heights, you'll notice that everything is regularly spaced, so we can easily find the equation of that line, which we're going to do in a moment. But first, I want to remind you that the term epsilon represents the random error. And that reflects the fact that y can vary for each fixed x. Now, if you go back to this chart, you'll notice that the weights seem to go up by 17 for every 4 inches in height. So we expect that the slope would be 17/4. Okay, so we expect that the slope is going to be 17/4. That's going to be 4.25. And we can find the intercept by just taking 2 of those points, only because they're regularly spaced. And we would find that calculating slope and intercept, that y would be minus 145 plus 4.25 times x. And that would be the line that best fits the data, plus there would be some epsilon to account for, again, the fact that y can vary for any fixed x. Actually, epsilon would be normally distributed with parameters epsilon for the mean, 0 for the mean, and sigma for the standard deviation. And once we have this model, we can predict the weights of people who are a certain height, for example. So let's say we wanted to predict what is the height of someone who is 70 inches tall. Okay, we could say that y of 70 would be minus 145 plus 4.25 times 70. And if we make that calculation, we would get that somebody who is 70 inches tall is, on average, 152.5 pounds. That would be on average. And that's how you can use the linear model to predict weights for other heights that we don't have data for.